teach. I'm not looking here to put anyone off the profession. That would certainly be a sign that I'd failed in making a good CPD. I think it's an important question to come back to from time to time, however. I think if we're brutally honest, there's a mix of reasons with us all, some more noble than others. We do need to pay the bills. And for some of you, like me, maybe you've taught all your lives and you feel there's nothing else you can do. What I'm really going to look at here, though, is what is the most noble reasons why you teach, and think teaching is a good thing to do. All reasons here are valid. None should be dismissed as negative, especially in the current climate. There really can be no judgments made. From the vast array of possible answers, I'd like to bring two answers to the forefront. To develop young people the opportunity and ability to be able to think, and to help young people be in the position where they can pick up marks in exams, which they need to better improve their chances in a successful future. I'd be keen to know what your reasons are, and would argue that apart from paying the bills and earning a wage, all the answers could loosely fit on a continuum between these ideas. Even words that relate to satisfaction, fulfillment, engagement, and even enjoyment are pretty synonymous with thinking and passing exams. Students who are not engaged, who don't have to think, are usually unhappy and often don't do as well in exams. I'd also argue, although it's a little off topic, that the number of people leaving or not wanting to enter the profession is a result of other things, making the job of teaching seem less about these things and more about those other things. I'd like to pose the idea that passing exams and thinking, although quite different, can be brought together with emphasis on the thinking. If students are taught and empowered how to think, they will pass exams as a natural result and receive enjoyment, fulfillment, and ultimately be engaged. But I know this is easier said than done. If students are just taught to pick up marks in exams, and this is the main motivation, the thinking may not, however, be as well developed. They will never learn to meet their potential. I think there's a huge level of trust in designing a curriculum that focuses on thinking and understanding with little emphasis on passing exams. There's a lot of trust in saying that students will naturally pass the exams if they are taught how to think, understand, and learn. This is, however, what I'm advocating, or at least steps in this direction, if an absolute philosophy is too radical. What percentage of students really benefit from being taught trigonometry? I honestly don't know the answer to this. I don't know if there's something to be said for a larger number of students being taught trigonometry because of its name, because of its reputation. Maybe for some students, withholding a topic with a grand reputation could be considered almost insulting. Maybe there is a cursory place or a light touch. Maybe there are easy marks that can be gained for some. I think the principles that underpin the teaching for mastery approach would very much suggest that if students do not have the prerequisite understanding to be able to move on to a topic, they simply do not do it until they are ready. The mastery approach would suggest that we go back and address fundamental areas before moving on. The responsive teaching approach would say similar. I think, to be honest, if a student was really struggling and if I wanted to bank marks in the foundation or the higher GCSE paper for them, I'd be tempted to go down the line of looking at topics that will generate students to think, to be engaged, and to lead to a deeper level of understanding and fulfillment before thinking about something new and arguably abstract. Without going down the route of trying to criticise schemes of work, I think it's fair to state a fact that I think is obvious. Not all students in Key Stage 4 are at the point where they get any benefit from trying to learn trigonometry in a robust way. They simply won't understand it. The question that needs to be posed: is there something more fundamental that will make them think, that will foster understanding, that will engage them better, that will have a bigger impact? If you're a teacher with a Year 11 class on a grade 4-5 boundary, if you know they can't do trigonometry and think there is a case that nice easy questions may come up and they could get a few marks and it's worth giving them a crash course on the basics, if that's what you're watching this presentation for, then this is probably not for you. There are better things that meet this purpose. If you're desperate to get your Year 11 class a grade 5 in 3 months and you're looking for a quick fix, maybe to tip this balance, this is probably not the presentation for you. There is no judgment. I think as teachers we've all done this. We have all used phrases like exam questions usually look like this, or if this comes up in the exam, just write this, or just learn it. Don't worry where it comes from, just learn it. There is no judgment. We are after all being held to account by numerous stakeholders to get results, and we have young people before us desperate, maybe not always desperate enough, to try and achieve big things in small windows. Anyway, this presentation or CPD is not going to give a quick fix. I'd argue that if you don't teach higher GCSE or A-level and your students are not likely to want to study A-level, then there may be things in this presentation that won't be relevant to your teaching. Questions may be posed such as, what is the point of them doing that? I think to us maths teachers, we are all too familiar with students asking things in the same way. But when quick fix, exam success is all that's on our mind, do we sometimes feel the same? How many students really come through our doors who need to truly understand trigonometry? Today's CPD is going to be grounded on the foundation that understanding for understanding's sake is both fulfilling and worthwhile. It is grounded on the belief that teaching for understanding will make students better mathematicians, better thinkers, better learners, and more engaged. It is rooted in the belief that quick fixes do not, in the end, lead to substantial successes in exams, real satisfaction, or learning in general, that the understanding and needing to think will lead to better outcomes in students. A skillful primary practitioner would never go down the route of saying 8 plus 7 equals 15, and this is one of several thousand simple calculations that you need to learn. Understanding is the goal from the onset, and with understanding can develop progression. 8 plus 7 is equal to 15 should be seen and understood long before it is learnt. 10 frames are the most commonly used thing to do this today. Teachers of early years and primary practitioners are very concerned with understanding. Arrays of 5 allow numbers to be seen rather than counted. You can see that 5 plus 3 is 8, and another 2 are needed to make 10, and that fills the 10 frame. There are 5 left over. I made the mistake earlier by referring to primary practitioners, but really, if any maths teacher spotted a student who couldn't understand why 8 plus 7 is 15, and we do know that there are students out there, then they would have a duty to go down this very route, or to use a similar representation to get some level of understanding of fundamental numeracy concepts. You may want to pause for a minute and look at the potential progression based on 8 plus 7 is 15. It is no way exhaustive. 8 plus 7 learned rather than being understood opens very few doors, since it offers no real thinking. I would put the argument forward that unless we are in a position where we can teach a topic for true understanding and link this to other topics, we should question what we are doing. We want to make students think rather than just recall processes. And if students are forced to think and understand, Even if this is in reference to a less advanced topic, their mental agility to relate, connect and build will increase. We are able to open doors to the next stage. The opposite may be true for trying to teach a topic students are not ready for. Doors close, self-esteem is impacted, nothing is achieved. I've chosen focus on trigonometry today, and I'm going to write a quote from an article from Spanberg in 2021. Due to the prominence of trigonometry in the mathematics syllabus and its applicability in different fields such as the teaching of conjecture and proof, in-school geometry, it is important that teachers should have all-inclusive understanding of trigonometry and be able to connect and present different trigonometrical concepts. Similarly, Kleichmann et al. 2015 said that pedagogical content knowledge influences key aspects of teaching quality, such as student gains in understanding mathematics. The study by Spanberg looked at 24 lessons, all on trigonometry. Lessons generally consisted of lecturing as the main teaching strategy. Only 18 of the 24 lessons included teacher-student discussion. Only 16 of the lessons included examples to explain the trigonometrical concepts. Linhart in 2001 acknowledged that good teaching and sound conceptual explanations are grounded on the use of examples. Only 2 lessons displayed reflections on misconceptions. Taylor in 2020 said teachers should have knowledge of curriculum that are in harmony with the goals of the curriculum. Thus, if the curriculum intent is to develop a shallow understanding that primarily focuses on students being able to pick up a few marks on easy exam questions, teachers must teach in a way that will achieve this goal. This CPD is not fit for that purpose. If the aim is for students to have a deep understanding that enables growth, the teacher's knowledge and teaching technique must reflect this in the classroom. Before teaching trigonometry, we need to make sure that the grounding is there. Topics I've listed here need to be secure. In my school, we've done Pythagoras' theorem in Year 8. Rounding would have been done in Year 7. The algebra where the unknown could be in the denominator of a fraction is Year 8. Inverse operations is Year 7. Ratio and direct proportion is in Year 8. And drawing and measuring lines and angles, Year 7. And just right before the right angle trigonometry, which we start in Year 9, we do similar shapes. Similar shapes and then trigonometry are the first topics we study in Year 9. Trigon, metron. What does it mean? What a lovely starter. Students can work out from the name where it comes from. The word trigonometry comes from the Greek words trigonon, triangle, and metron, to measure. It is notable, even before the topic is announced, we want students to think. In many ways, I prefer to project this than a learning objective or a title. Make a scale drawing to find x. If students can't do this, they should not be doing this topic. I'm using pretty basic fundamental skills and practicing accuracy and trying to get students to think and conjecture. I want them to ask me, is it 6 centimetres because it's half of 12? I don't want to tell them. Although there is nothing wrong with me delivering such maths with a PowerPoint, I want to be fully adaptive. I may need 2 more examples. I may need 5 more examples of this to get the idea that the side opposite of the angle is half the length of the hypotenuse for a 30-degree angle in a right-angled triangle. If students conjecture about the other side's length, I will let them explore this. If they want to explore different angles and come to the conclusion that the ratio of the hypotenuse, that is opposite, increases as the angle increases, there's room for this. I want students to explore, conjecture and build understanding, not process. I'd like to hope questions were also being explored about the opposite. Can the hypotenuse be bigger than the opposite side? Or can the opposite side be bigger than the hypotenuse? Is one always true? The idea that this is a right-angled triangle is established through this, and the language I use is well established. I want the class to see something like this and say, these are similar triangles. For an angle of 30 degrees, the side opposite the angle is always half the hypotenuse. If we've just done similar triangles, they're very quick to make this connection. They're very quick to make the connection that ratio and trigonometry are essentially the same thing. I will try and guide them towards the use of fractions where possible, and whatever I write down will be a fraction. I will use the word ratio when I talk about it. I will say the ratio of the opposite and the hypotenuse is 1 to 2 for an angle of 30 degrees. The language the class sees me use will become their shared language. I will vary the angles slightly. 30, 53 and 64 degrees give some nice angles that produce nice approximate numerators with a hypotenuse of 10. On a side note, one of the 5 big ideas within maths mastery is variation, keeping some things the same and letting some things differ. We previously kept the 30 degrees the same and varied the hypotenuse. Now we're keeping the hypotenuse the same and varying the angle. When students share results individually or collectively, I will correct or acknowledge that yes, an angle of 64 degrees seems to produce an opposite side of 9/10 or 0.9 the hypotenuse. Now it's time to ask questions more generally. What happens to the ratio of as the angle increases or decreases? We want to get the idea that angles can go as far as 90 degrees and the length of the opposite side gets closer and closer to the hypotenuse, but never exceeds it. In a similar way, the length of the opposite side is very small compared to the hypotenuse if the angle is very small. So the question is raised with these values and possibly a few more. How can we find a way of looking at these angles and convert them to a ratio that we can use to calculate lengths? If a student has not already reached for their calculator, then a quick prompt will allow students the opportunity to discover the sign button. Let them explore this and teach them key features. For example, sine 50, 30, 45, 60 and 75 seem to give exact ratios, some involving surds and 30 being exactly a half. Make sure they can convert these to decimals on their calculator also. Explain that sine is short for sine, and a sine is a geometrical length connected with a circle. In my curriculum, we explore this in year 10 when we look at the trigonometric graphs and angles above 90 degrees and below 0. Show them that sine 30 is 0.5 and that the inverse of sine of 0.5 is 30. Let them explore and give them time to learn these skills. A few non-triangle related questions may also be appropriate for students to learn how to use these buttons. It may be appropriate for some practice on rounding answers correctly, not straight from the calculator. It will also be worthwhile letting them know that angles here are measured in degrees. There are other angle measurements used, such as radians. Students should know how to change settings and check their calculator with sine 30. I think the history of using tables before we had calculators is a wonderful hook. I have a book which actually dates back and shows how tables would have been used. But you can easily get things from the internet or show things such as what I've projected here. It's interesting to note here also that the angles they have a minute by them, so they're not decimalised, and that is historically how angles were looked at. I'm going to talk a little bit later about the Babylonians and the base number system, which has a base of 60 and why we have 360 degrees. But it's all connected and it all adds nice things which help enrich students and draw them in and understand things better. We need an example now. We need an example to be modelled by the teacher. I'm a very big advocate of all algebra and all calculations being done by hand. So although I will click through some solutions here, in front of a class I would expect the teacher to physically write it down and show the steps and talk through the different parts. I also want to put in here that I've put my two values to three significant figures, and that means that when I have a solution I can talk about it being correct to three significant figures. Sometimes I feel uncomfortable with answers where things might just be to one significant figure and then we're not quite sure about accuracy at the end. So first of all, I'm quite happy with sine 35 is x over 12 as a first step. I'm quite happy with that. At the moment we've only looked at the sine function, so it has to be the sine function. So the ratio here is equal to sine of 35, and that makes perfect sense. If I was doing this myself, that would be my first step. I don't expect anything different from the students. Quick rearrangement, and then we have our value, which I would get the class and I would write down myself truncated to at least 5 digits. This is likely to get them full marks in a lot of cases if we're going to examine them, but we're moving away from this idea of rounding. We don't round things midway through a question. We don't round straight from our calculator. We write down the solution we've got and then we take a moment to think about rounding. Maybe the question says round to three significant figures, so we do so. In this particular case, it doesn't say anything, and I don't think there's any need to round. But three significant figures would be the absolute maximum we'd want. Our units are centimetres, so in a final step when we think about rounding, we may write that down. We may also check, is our answer sensible? The class have talked about 30 being half, or having a ratio sine of 30 seems to be a half, so this seems like a very sensible answer. And modelling that as a teacher and getting the class to make that thought process, I feel, is very important. So now I've modelled the question, and maybe I might need to model some different ones. Maybe I need to model some with the unknown in different places. But I think in a way that's depriving students of the opportunity to work themselves now. They shouldn't be doing trigonometry if they can't rearrange equations where the unknown is in the denominator, for instance. So I would let students work, but perhaps work at a pace that's appropriate to them and the class, giving them the correct amount. All my examples still just involve the sine function though. It's just getting really confident, and I would like to include in there some application problems as well. I've wrestled with the idea of whether or not it's appropriate to use Greek letters in angles. Sometimes I think that maybe that just confuses it if students might be anxious, but I've kind of come to the conclusion that I don't really think it matters. But some discussion of what Greek letters are and why we use them and what we call them is needed if this is the very first time we're exposing students to that. Again, I'm using a mastery idea here that we don't move on until we've developed really deep understanding, and that's why at this particular point I still haven't introduced the cosine and the tangent functions. I'm still just looking at the sine function. However, I realise there's many ways of doing this, and I have no problem with it being done differently. In this particular one, we're asking, is the triangle right angled? Is it certainly right angled? There's some reasoning that needs to go on there as they work out values, but that reasoning, I hope, would allow students to articulate an answer which involves the word ratio. If I've done what I wanted to do, that word ratio should be there, and there should be some clarity. But obviously answers such as sine of 64 does not equal 9/10 would be absolutely sufficient. We're on the theme of trying to reason and trying to think. So here are a set of questions. This would be a nice slide to show a class. If theta stays the same and y increases, what happens to x? Theta stays the same and x increases, what happens to y? If x stays the same and y decreases, what happens to theta? What happens to sine theta? Those are all really nice questions that could be posed as discussion. Perhaps they could be as extension for some students, but it's trying to get thinking into what we do, not just mechanical procedure. There should be no surprise that after a period of time spent looking at just the sine ratio, the cosine ratio can be explored, and the adjacent side, because it lies next to the angle. I repeat the word and how I locate it verbally as many times as I can. This reinforces for students how to locate it. I'm perhaps a little less perceptive of how this is developed, and I think it depends on the class. Maybe the exact same development is needed as the sine function to start with. Drawing the diagrams to scale, looking for patterns, looking perhaps at the angle 60 being particularly useful. It will certainly work and certainly cause that nice link between trig ratios and similar triangles. I would hope that a class who fully understand where we have already come from will quickly recognise that the triangle here is the same one as they have already met, since the other angle is 30 degrees, because the angles in a triangle add to 180. Therefore, they can already solve the problem, and why not let them try on a mini whiteboard or the back of their book? The question can then be formed, is there a quicker way of looking at the ratio between the adjacent and the hypotenuse? Is there a ratio that can be found here? It is likely that before you even have time to develop the idea, students will know it is cos. Maybe they will need some time to play with their calculators. Explain that cos comes from the term cosine, which has the etymology of the complement of the sine. Complementary angles are historically, not too long ago, used to describe exactly two angles that sum to 90 degrees. On a side note, it is worth mentioning that supplementary angles describe exactly two angles that add to 180 degrees. If students have been confident with the sine function, they will now easily be able to transfer this to the cosine function, and some practice will follow. In my experience, by being very careful about looking at whether it's the opposite or the adjacent side that is being looked at, students can mix between questions fairly fluently and fairly easily without much more needing to be modelled. The slide here very similar to the one before, obviously involving the cosine function. And again, spotting patterns is very, very important here, giving students the opportunity to realise that this time as theta increases, the value of x decreases. That's going to link very closely to a good understanding of how the cosine function works and how the graph works. And that's very different to how the sine function worked when, as the value of theta increased, the sine of the opposite side also increased. So the cosine seems to go down. Ideas of proportionality are made. Not direct proportionality and inverse proportionality quite, but those relationships, those mathematical relationships are key. I make no apologies for advocating additional algebra and additional abstraction. Students will develop at different levels, and choosing the right time to add challenge to both individuals and classes is a difficult skill for us all. The gulf between GCSE and A-level is massive. If we don't commit to trying to make sure that algebra is used to the maximum capacity that is appropriate to students, we are doing them a disservice. Coming back to the theme I presented earlier, if for the last question students can't reason that sine of x is equal to cos of 90 minus x, then this shows they don't understand trigonometry. If they can't form and solve a linear equation in one unknown, that's shown in the third question down, then there is the question, why are they studying trigonometry at this point when they can't solve equations with one unknown? We do want to pose questions that make students think, that challenge students, and develop understanding. When the cosine and the sine functions are mastered, it is just the tan function for the moment we need to look at. And it is likely that students will be able to work with problems on the tan function with very little input. I'd probably model one example so that students have something to follow. Students will now be procedurally able to solve problems, and they might be becoming quite mechanical in their methods. They may have lost the idea to some degree that the trig functions, including the tan function, is a ratio. Exercises that give them the opportunity to think are very, very important. And there's a slide here with some lovely questions, just looking at a little bit of variation, varying one value, seeing what happens to other ones, what happens about isosceles triangles, does that lead to any results that are significant? And what's the biggest value of tan theta you can find? And again, there's lots of nice things to play with there. Again, some lovely questions here. Would they all be appropriate for students just at the start of trigonometry? No, I'm not trying to argue that they would be, but they could be. Do they require students to show understanding rather than just procedural recognition? Definitely yes. And do they frame trigonometric functions as ratios rather than tools to solve problems? Yes, definitely. And I think questions where we actually challenge students to draw diagrams is very, very important. To try and draw diagrams, to try and make concrete representations of what the abstract is. Our strongest students must not just become very confident in procedural maths, and they must be able to work from the concrete and be able to have representations for what is abstract. Quite often we do representations for our weakest students to help them understand and deepen their understanding, but the strongest students need that just as much. Moving back more generally, students need to practice, and they need to solve problems in as many contexts as possible. Notice that as a teacher, I rarely refer to trigonometric functions without adding the word ratio. Even when students are procedurally fluent, they will be reminded of what trigonometric functions really are. I've not overtly mentioned SOHCAHTOA. And I certainly don't draw triangles such as the ones on this page. I don't have an objection to SOHCAHTOA. If they have been taught to understand, they can use acronyms and use things to help them remember, to help them get it right. I do object to the triangles, however. If students can't rearrange formula, then why are they doing trigonometry? If students can rearrange formula but sometimes get it wrong, then why not give them every chance to practice? I have no objection to triangles being labelled with hype, op and adj, if that's the way students are going to do it and do it consistently. But we would hope students would get to a point where they practice sufficiently and that's no longer needed. To add some more detail about our Year 9 unit, at the beginning of the year we include revision of Pythagoras' theorem and embed some trigonometric work there. So we may say, given sine of x is a half, find the exact value of cos of x and tan x. This is obviously a known angle, 30 degrees, but we do similar questions using surds and exact values, such as if tan of x is 3/4, what's sine of x, what's cos of x. Using trigonometry in the context of bearings is also covered in Year 9. It is common here for students to need some recap on bearings and general, including on rounding and how we round things nicely. Angles of elevation and depression are also discussed, and as much context is given as we can make. We consider problems where trigonometry and Pythagoras may be used multiple times, or right angle trigonometry can be used to split up non-right angle triangles. That is pretty much our Year 9 curriculum though. I'm not saying that that should be a Year 9 curriculum for every school, but that's the point we got up to in Year 9. We're now ready to move on to Year 10. So in Year 10, we now look at exact values. We look at trigonometric graphs, and we use some trig equations. We probably look at equations in a way that tries to start preparing students for A-level a little bit more. It's not just for the GCSE exams. And then in a later unit we do sine rule, cosine rule, and area of a triangle. Don't just do the derivations for the class and then say, here are 9 different things, learn them. Let the class explore them themselves. Let them work them out. It would be a valid question to ask if the class can't work these things out with investigation, maybe with a bit of guidance and a bit of pushing in the right direction. Why are they doing this topic? Why is it relevant to them? How is it going to help them? It shouldn't just be about learning by rote 9 different things, or perhaps giving special tricks to try and learn them in an easier way. There should be some level of understanding in the topic. But yes, I am an advocate that they should be learnt, and I am an advocate that any way that helps them to learn them will be valuable. But if they haven't understood them in the first place, there's not a lot of value in them being learnt. According to Wong in 2012, by using real-life examples, teachers are not only advancing students' critical thinking skills, but also developing their own higher-order knowledge. Trigonometry is widely used in engineering, architecture, music, and industry to describe the relationship between angles and lengths of triangles. For example, trigonometry is often used to determine angles of elevation for heights of buildings, angles of depression for depths of underground systems or roof inclination. Trigonometry also plays a major role in flight engineering to navigate planes using sine, cosine or area rules, and in the music production where sound waves are displayed graphically by sine and cosine functions. To introduce real examples into the teaching of trigonometry, Golden-Schmidt 2010 suggested that students be asked to design simulated word problems about real-life situations and apply trigonometric functions to solve them. Another method to make trigonometry meaningful, according to Carson in 2017, is to review the history on discoveries of measurements of chords in circles and properties of triangles, and then map that with trigonometric content prescribed in the curriculum. Nevertheless, these examples, teachers need to select teaching strategies appropriate for the context that they will teach to ensure maximum learning by students, but also developed knowledge of teaching strategies. Trigonometric tables were created over 2,000 years ago for computations in astronomy. The stars were thought to be fixed on a crystal sphere of great size, and that model was perfect for the practical purposes. Only the planets moved on the sphere. At the time, there were 7 recognised planets: Mercury, Venus, Mars, Jupiter, Saturn. The Moon and the Sun were also considered planets. Those are the planets that we name our days of the week after. The Earth wasn't yet considered to be a planet since it was the centre of the universe, and the outer planets hadn't been discovered yet. The kind of trigonometry needed to understand positions on a sphere is called spherical trigonometry. But it is easy to see how right angles can be embedded into a sphere, or indeed a circle, which is any cross-section of the sphere. The word chord refers to a straight line drawn between 2 points on a circle, or more generally on any curve. The known first trigonometric table was a table of chords by Hipparchus in 190 BC, produced the first trigonometric table for use in astronomy. In modern times, the sine is used instead, which is, in a circle, half a chord. I'll show you a diagram of this later. The ratio between the length of the chord AB and the arc of the chord AB was the element of interest. There is no coincidence here between arc chord and arc sine having some reference to an angle for those who are familiar with the way inverse trigonometry functions are used in A-level. Later, Ptolemy, in 100 AD, constructed a more complete table of chords. His table had chords for angles increasing from half a degree to 180 degrees by steps of half a degree. All calculations were in fractions because decimals were not used. In many ways, I like this since it preserves the idea of ratio very neatly. To maybe oversimplify, as I best understand it, an observer on Earth would see a star moving across the arc AB with respect to a chord AB. Arc AB, however, would be observable and measurable by this chord. I personally love the history of mathematics, and not surprisingly, many children do too. Not always the ones who are always procedurally most confident. The word sine comes from the Latin sinus, meaning a bend, which in turn comes from the Sanskrit word jiva, meaning a bowstring. The word was originally applied to the line segment AB in the figure shown. You can see how this could be called a bowstring. The ratio of the sine AB to the radius of the circle OA is the sine of the angle AOB. It is notable and exciting at this point to observe that OB is the sine of the complementary angle of AOB. Complementary of sine is cosine. And if the angle were in radians on a unit circle, AC would be exactly the arc of the sine. But I would not mention this in year 10. This would wait until A-level. A tangent to the circle at A, meeting an extension of the radius at D, corresponds to the tangent of angle AOB. I have a beautiful animation programmed in GSP of a point moving about a unit circle and the variations in the sine, cosine and tangent with occasional moments. At 90 degrees, when the tangent is seen to get larger and larger, and then it shoots off to infinity. The graphs of all three functions are plotted by these lengths in real time. Although I know I'm giving a lot of information that may sound abstract, historic, or obsolete now, but how can we expect students to understand the graphs of sine, cosine, and tangent functions if we leave them in the abstract and inaccessible world? How can we expect them to get excited about mathematics unless we ourselves can get excited about mathematics in all its different elements? One of the 5 big ideas from the Mastery programme of helping students to understand mathematics is to use visual representation and manipulatives. This is not just to support students to grasp basic concepts. This is to support our most able students to be the very best they can be and master the subject with no restrictions or boundaries. In Year 10, at my school, we look at trigonometric graphs. Bearing in mind the historical relevance of having planets going around a sun or planets going around another planet in respect to how it actually was thought of then, I get a large piece of paper and I put that on the floor. I actually use wallpaper, so it's really, really big. And I get the whole class to gather round. I have a program in GSP that does almost exactly the same, but I quite like the kinesthetic idea of doing it as an investigation with a class without pre-programming it. I like the way I can be responsive and answer questions and deviate questions and go at a time frame that suits the class. I model a planet going about the sun, and I set 2 students who are both perpendicular to the system to look at the system. At one point, the planet would be invisible because the sun would eclipse it and make it impossible. And at another point, it would be at its full orientation to the side. Let's call it a distance 1. I tend to call the distance maybe 1 billion kilometers, be fairly generic. It could be any planet in any solar system. I move the planet around at a pace that I think the class are engaged by. I move it first to 30 degrees. When the planet has moved 30 degrees, I talk to the 2 people and what they can see. What movements have they seen? Person A might see that at 30 degrees it's moved from 0 to 0.5. And the other person would see, well, no, it's been at number 1 to start with, and then it's gone to 0.8. So both of them are correct, but they're seeing it from a different perspective. I then move it to 60 degrees. And I ask both people what they've seen. Maybe in the room somebody else, or maybe myself, I have a table of values on the board and I fill in some of the values that were observed. Maybe someone else draws a graph of this, or maybe we'll draw a graph of it together afterwards. But the class are seeing that as the planet moves through these angles, different observations are seen. 90 degrees, person B might see there's actually no movement at all. The planet is right in front of the sun. In fact, they may not even be able to see the sun properly. It eclipses it. Person A, on the other hand, sees something completely different. It's at its furthest possible movement away from the sun. It's ready to start moving back in closer. And suddenly our trigonometry from before, which was limited to a right angle triangle, becomes relevant. We're moving beyond 90 degrees and we're saying, how can that be defined? I will be drawing triangles as I do this, and I will be labeling the sine as a geometric line and measuring that sine. We move now to 120 degrees. And we suddenly see that the cosine angle becomes negative, starts to have a negative displacement. And indeed, that's how the graph will start to look. Maybe there's an opportunity now to look at calculators, to look at cos of 120 and cos of 150 and see that those show different values. Maybe this is the time to look at sine of 120 and see that that gives us the exact same value as sine of 60. And sine of 150 gives us the exact same value as sine of 30. Quite often the sheet of paper I have on the floor by now has lots of triangles drawn, lots of calculations drawn, lots of various notes. Class have asked things and I've wanted to point things out, but it's been a true investigation and an investigation that's worked with the class together. As I said earlier, I have done this with GSP and it has had a lot of impact as well, but it's much more restrictive in that case because I've already made it all. I'm not going at the class's pace. I'm doing it for them like this. We're working together as a team. So for the rest of year 10 trigonometry, I'm a lot less prescriptive in terms of how it's delivered, but I've got ideas that I'd like to share, which you can discern whether or not they will work or be relevant for your groups. Firstly, keep angles close to 90, 45 and 60 degrees, at least for some of the time. This encourages students to estimate and check solutions and think. We want our students to ask the question as to whether a result is sensible. We have to give them the opportunity. With equilateral triangles or 90-degree triangles where there may be Pythagorean triples, this gives them that opportunity to check answers whether or not they're sensible. If in the given triangle, using variation, we change 6.2 to 5.7, we will see that the value of theta falls below 60 degrees. If we want students to understand the sine rule in particular, they should see that increasing the side opposite the angle increases the angle. The reverse is also true. In fact, the sine rule moves from being an abstract formula that can only be convincing after formal derivation to a simpler matter of understanding connected with ratios in a triangle. A technology such as GeoGebra would certainly allow this to be seen. But why not allow students to discover it by your choice of examples? These need not be on a PowerPoint or worksheet and can easily be created on the spot. There is room here for students to first-hand see that the cosine of an obtuse angle is negative, reinforcing what we've previously learned by the graphs. There is also, with various triangles that are close to being right-angled, to understand Pythagoras' theorem as a special case of the cosine rule. So, a really radical idea that does differ from convention. Do students need to spend a long time writing down formulas for sine rule and cosine rule? Do they need to label the triangle at all? I would argue no for both, although I would add a caveat that Edexcel did state that they may award method marks for students demonstrating intent in writing a formula. Firstly, if a triangle was labelled as the one already given in the diagram here, we tackle immediate problems. Secondly, we clog students' brains up with learning formulas rather than understanding relationships. I have seen non-right-angled trigonometry taught with teachers giving 6 formulas for cosine rule, each with different letters, and some of them making the angle subject, and 2 rules for sine rule, the second being its reciprocal. I've then seen students trying to learn by rote 8 formulas. If a student is not able to manipulate a formula like cosine rule, then I'd ask the question, why is this topic being taught at all? If a student is unable to solve an algebraic equation with the unknown in the denominator, then why on earth are they doing non-right-angled trigonometry? When my department teach this topic, we use the term trapped angle, and students are immediately looking for a trapped angle. This is not a new term for students either. In Year 7, when we practice constructing triangles using a protractor, ruler and compass, we see we can construct triangles in the form with a side, an angle, and a side with a trapped angle. In a way, that is unique. It's congruent. We see that a triangle where we're given side, side, side also creates a unique triangle with angles that can be checked and measured. In a similar way, in Year 11, when we look at the rules connected with triangles being congruent, we make the connection with constructing triangles in Year 7 and non-right-angled triangles in Year 10. I'm not saying never learn formula, and I'm not saying that labelling triangles is always a bad idea, but I am posing the idea: is it always necessary, and does it need as much focus as sometimes we give it? Here is another nice example where students should be able to estimate an angle, a possible angle, is close to 67 degrees. But here I have given side, side, angle. The angle is not trapped. Is there another solution? I'm not saying at GCSE this should be fully explored, but I am suggesting it shouldn't be fully ignored either. There are opportunities embedded here to reinforce understanding of triangles, construction, congruence, and drawing geometrical representations. There's also opportunities for creating misconceptions if we just ignore the fact that there may be a second solution. Although it's not formally part of the GCSE or A-level curriculum, I think that understanding triangles in all the different scenarios they are presented is somehow very, very important, and perhaps sometimes something we miss. Here's a nice example with the idea that we'd like students to develop their ideas of reasoning. Give 2 mathematical reasons why this triangle can never exist. Hopefully, especially in Key Stage 4, students would start looking at Pythagoras' theorem and come up with the argument Pythagoras' theorem is not satisfied. But I think a much deeper answer and a much more impressive answer would be the third side of a triangle can never be greater than the sum of the other 2 sides. This is a theorem that we don't usually teach. It's the triangle equality theorem, but it's quite fundamental in understanding triangles. So my final GCSE reflection is this: use the words. Just work out something, then look for something else. I regularly fall into the trap of telling students what to do too quickly. This is a trap that starts as early as Year 7, when I just start looking at simple angles. I've observed many other teachers make the same mistakes as me. If I don't tell them what to do, they will become unhappy and go off task. Yes, we must consider this and look to develop a culture where students need to think. And it doesn't happen overnight, and there are limits. If, for the example above, you would be tempted to point out the angle opposite the x and say use sine rule to find this, then angles in a triangle, then sine rule again, maybe this is a problem that's not appropriate for the class at this stage. I'm always sceptical of the use of scaffolded worksheets or help cards if they remove the opportunity for students to need to think. If this problem is inaccessible to someone in the class, then give them something that they can access that will require them to think. There is an argument for giving students practice to gain confidence and then making them think that thinking must always be the motivation. I'm putting these ones here as a bridge between GCSE and A-level because they're very suitable for A-level and maybe for most students at GCSE they're pushing it a bit too far. But there's so much reasoning there and there's so much exploration of notation, such as when we square something trigonometric, where does that index go? Is it the same as squaring the angle? If we're solving a very simple trig equation, do we get more than one solution if it's got a squared in? If it's a quadratic trig equation? If students understand that normal equations that are quadratic have more than one solution, could we ask, even at GCSE, some of these questions? Can they be explored? So for A-level trigonometry, I'm going to be even less prescriptive and just share some ideas, some things that I feel are worth mentioning, but maybe something different to other people. Maybe they're challenging ideas. Reflection 1. Calculators sometimes do more harm than good. I strongly believe this. Every student that I have ever taught who I consider to be an excellent mathematician at the end of year 13 can, with reasonable accuracy, state the value of things such as cosec 120 without a calculator. Maybe this is down to sufficient practice. Maybe this is down to memory being a factor. Maybe I've laboured this point and they have simply listened to what I've said and made a note to try and learn things like that. The mental process of saying cosec 120 is the reciprocal of sine 120, and sine 120 is the same as sine 60, so this must be root 3 over 2. I think I've accepted that I cannot police the use of calculators for such things as much as I would like. Maybe in exams I'd rather risks not be taken, but at home and in class, this mental reasoning is building up a maths brain based on understanding. I know it's not a battle that can be won for all students, but your choice of examples should include at least some trigonometry work which does not require a calculator. Reflection 2. Cast, graphs, or something else. In solving trig equations, I started my career using cast. This was also the way I learned in school. My current school adopted a policy of sketching the graphs rather than using cast. And I will note, although not as quick, I quickly became a convert as it required students to think more and sketch graphs, something that I always worry students are reluctant to do. Now we've agreed to do something far more efficient. And after, and only after, the graphs are fully understood, we have suggested that sine, cosine and tangent each have a very simple rule, which is easily derived from the graph and which can be remembered as a way to solve equations. I will show you a solution on the next slide. So here is a trig equation, and I'm just going to go through the steps on this slide. In the classroom, I would always write this on the board and model every step of it, talking through. Obviously, I can't do that right at the moment, but I really think it's bad practice just to click through slides when we're in front of students. So the first stage of a solution would be to get our first one, which is the 30 degrees, which I'd hope a calculator wouldn't be necessary for here. Now the next one for 150, and this is a point that needs discussion, to talk about the graph and to see that, well, that's 180 minus the 30. I'd like to think that for sine, cosine and tangent, these can be learnt with practice. Students don't need to draw the graph. That first two solutions can be obtained really easily. Then from there, we look to obtain other solutions. Experience tells us how many to go for, but here we've added 360 onto both of them, very simple calculations, but it may be necessary to go back as well, to take 360 away. Students end up doing just the right number of times after a little bit of practice, but the work is laid out exactly like this. First solutions and the columns are neat. After they've solved those equations, which are all easily done in single steps, they're all listed, and then you can reflect on which ones are in the interval. For my better students, they wouldn't have even got the first and last solution here. They'd have immediately saw them. But in the first days of doing this, it takes a while to get that instinctive kind of connection that here there'll be 4 solutions. So then we list the 4 solutions. We then check the solutions to make sure they satisfy the original equation. And as teachers, it's very important to model that we do that at every stage of algebra. If there's an equation that needs solving, especially if we've got a calculator, that is one good way a calculator can be used to check solutions. So I'm going to model the first stages of a cosine function as well. So most students for this one would use a calculator, although I would hope my better students would not. They would get the first solution, and then the second solution, regardless of what it is, even if it's a negative number, will be subtracted from 360 because of the symmetry in the cosine graph. That needs to be understood before anything is learned. But from this stage on, you can immediately add 360, add 360 again, or take 360 if necessary to all the solutions, and then solve them, look at which ones lie in the interval, and pick them out. The tan one is possibly the easiest one, and I don't do a lot of ones that require a calculator and require decimals, but I thought it was worthwhile doing the first stage here, that we would do the inverse, and then we know that it has a period of 180. So we get our first solution, we add 180 on. I don't necessarily use the word principal value. I know there is a definition for that. I think it's just the routine and the process, and students do move on to that very quickly. They end up just getting that idea in place. That for the sine, we subtract the first from 180. For the cosine, we subtract the first from 360. And for the tan function, we just add 180 on. When we move to radians, it becomes really simple, moving it from pi to 2 pi. I encourage students to know their trig identities, to write them all down from scratch, without having to use a formula booklet. They can derive them as they're doing them. I know that 3 Pythagorean ones flow one from the next one. The double angle formulas can be taken very quickly from the compound angle formulas, which should be learnt, although they are in the formula booklet. And then the 3 different forms for cos 2 theta should be there. Sec, cosec and cot, again, can be recalled just by looking at the third letter. I mean, they should just become instinctive fairly quickly. The best students, on repetition of writing the whole list, they become able to pick out the right one and use the right one correctly. But all students then have a mechanism that they can follow. I'm using a very similar mantra here to what we said in Key Stage 3 and Key Stage 4. If you don't know what to do, do something. When we're trying to prove trigonometric identities, allow them to play, allow them to fail. I think there's an awful lot to be said in maths for allowing students to fail. I think topics like integration are a brilliant example of that. If we don't allow them to try things out and see why things don't work, if everything we do is, if it looks like this, do this, if it looks like this, do that, then we're not encouraging them to think. And thinking is the key to becoming good at maths and understanding maths. Continuing from a similar slide I showed regarding Key Stage 4 trigonometry, the way we define the sine of a circle as a geometric line rather than a function, and the complement of the sine, the cosine, as being the corresponding geometrical line which is perpendicular to this, students need to know, not because it's going to be examined, but because it's interesting, that in geometry a secant is a straight line or ray that intersects a curve, such as a circle, at 2 or more points. The word secant comes from the Latin word secar, meaning to cut. In the case of a circle, a secant intersects the circle at exactly 2 points, and the line segment determined by these 2 points is called a chord. In trigonometry, the secant of an angle in a right-angled triangle is the ratio of the length of the hypotenuse to the length of the adjacent side. The cosecant is again the complement of the secant, and the cotangent can clearly be seen on the diagram. GSP can be used beautifully, showing us a point moving around a circle, having the graphs of all of these functions coming up and little tables of values, but you can really understand all 6 trigonomic functions through there. And there are more than 6 if you look back historically, which may also be something you find interesting. Returning back to the diagram from earlier, where I would hope students from Key Stage 4 would already have some realization that there is some relationship between the sine, denoted AC, and the arc AD that corresponds to the sine AC. This relationship was historically the relationship that was first tabulated in trigonometry. Angle measurement at this point was not properly defined. If we take the circle to have radius 1, and we use the correct definition of a radian, the angle subtended at the centre of a circle by an arc equal in length to the radius, we quickly see that by this definition, or L equals r theta, that the arc of the sine is the angle at the centre in radians. The beautiful etymology of arc sine, arc cos, and arc tan is revealed. I hope that this, coupled with the historical use of why the Babylonians adopted a number system based 60, which is why there remains 60 minutes in an hour and 360 degrees in a circle, interests and inspires a number of students. My thoughts on A-level have been less exhaustive than Key Stage 3 or 4. These are mainly designed to embellish some topics with some thoughts that I think may be different to what is found in a bog-standard textbook. I hope they have been some use, however, and of interest. I think a topic such as trigonometry is too big to say this is how it should be done. And we all know that classes are different and students are different, and one size suits all does not work. Maybe some of the reflections I gave for Key Stage 4 trigonometry would be better used in Key Stage 5. Why do we teach? This was my first question today. We talked about making students think and helping students pass exams. I hope that my presentation has kept these 2 important ideas closely knitted together. I hope there is something you can take away that will help you to plan lessons, sequences of lessons, or build a scheme of learning in a way that develops thinking, enjoyment, engagement, and fulfillment. Any feedback would be gladly accepted, and thank you for listening to my presentation.